Standard life. So last week we finished implementing our interpreter, and it works fully. Now we're going to start on a more ambitious journey, namely implementing a virtual machine and then compiling Simplang code for that to that virtual machine. And but before we do that, we should maybe even figure out why we're trying to do that in the first place. There's two reasons. The first one is that our goal ultimately is to write a compiler that compiles to native machine code to get maximum performance, or maybe not maximum performance, but good performance, and we want to learn how a compiler works. And writing a compiler for a simple virtual machine is an easier first step. But the second is also that we kind of want to have a faster interpreter. And we can actually, one thing we can try to do is, and I did that recently. I'm going to see if I can make that work again. We can profile our interpreter and see where it spends its time. Simplang, yes. So this is Xcode. I'm just going to use the Xcode performance analyzer, which is instruments, which internally uses dtrace. What is that? Oh no, I don't want to analyze profile. I wonder what it told me. Anyway, so we're using the time profiler. So the way the time profiler works is that basically at regular intervals, it looks at either a single process or all the processes that are running on your system, and it gets a stack trace of that process. So basically, a trace that shows which functions are currently running or are being executed within that process, and then it builds a histogram of those. And so the idea is that if you spend a very long time in one particular function, then that function will show up a lot in the trace, right? Because you're sampling it at regular intervals. So it would be really weird if that didn't happen. So you get a pretty good idea of where your program spends time, not necessarily why it spends time there. That you have to figure out yourself. So we're going to start that. And
how does it know like how much time it's spent there if it's just doing histogram?
Well, if your program works for 10 seconds, and let's say it does 100 samples per second, right? You get 1 million samples, and if 500,000 of those samples it catches your program in one particular function, then your program probably spends about half of its time in that function. Mm-hmm. Does that make sense? Yeah. And you can actually get even more detailed information, because it cannot just tell you which function it's in, but it can tell you which part of the function it's in. down to actually which machine instruction, which is sometimes a little bit problematic because CPUs work in very complicated ways, and the instruction where it shows it's spending the time in might not actually be the reason for the time spent there. It might just be that for some reason it's waiting for, I mean, that's usually what happens. It's waiting for something to come out of memory. And then that thing ends up being the thing that holds it up. And so a different instruction shows up. But yeah, let's run it. So I'm running next prime with, I don't know, some large number, and it should run for a few seconds, and then we'll see what happens. That was a little short, 2 milliseconds, really? Why don't I believe that? Wait, what is that?
You have to like put it in some weird
No. Choose target, edit sim plan. Why is that suddenly gone, the next prime? And why the hell? Yeah, choose. This is really weird. What is that? Oh, that's the working directory. Why did that suddenly go away? That is so weird. So I want Dropbox, work, simplan, examples. I want this to be the working directory. So I want it to go here, and I want it to run next prime .sl. Let's see how long we can make this. This takes about a second. This takes about 5 seconds. Okay, that's good. So I wanted to run with these arguments. Choose. Okay. All right, now it's running. So now what you usually want to do is you want to invert the call tree. If you don't invert the call tree, then it will tell you, oh, it's running on the main thread and it's spending its time in start, which calls main, which calls eval function, which calls eval expert, which calls eval, which calls eval function, which calls eval expert. But that's not what you want to know. You want to know which is the function that's actually at the bottom, like that's actually doing something as opposed to just calling other functions. So you invert the call tree. And one thing that we're seeing is, first of all, it's spending about 36, so about a third of the time in eval itself, which is where we're actually doing work. Then it spends a lot of time in malloc. So all of this is malloc. This is probably also called by malloc from somewhere. See, as you can see, this is called from malloc. I don't know why eval is calling a spin lock. Doesn't quite make sense. This is more malloc. Then we're spending about 6% of our time comparing strings. Then we're more malloc, then free. And like this is basically peanuts. But as you can see, is we're spending only about 1.2 seconds really doing work, and the other stuff is allocating memory, comparing strings, doing other not very useful stuff. So we want to do away with things like dynamically allocating memory, clearly, because that's costing us a lot of time. We also don't want to compare, or we don't even want to search for variables in the first place, much less compare variable names at runtime. All our variables, thankfully, have very short names, but imagine we had super long variable names, then it would spend even more time in string compare. But there are ways in which we could extend our interpreter to do those things less, or maybe not at all anymore. But we would still have one fundamental issue, which is a little bit harder to profile, which is that we are operating on a data structure that is linked together by pointers, where each single thing is just a little tiny piece of information, like, oh, you need to add 2 numbers, and here's a pointer to another data structure that tells you what the first number is going to be, and here's another pointer that tells you what the second number might be. And so that is generally pretty inefficient compared to just reading memory sequentially, which is, for example, how like actual machine code is organized. It's just one instruction after the other sequentially in memory. And as long as you're not doing any jumps or calls, you're just going through it linearly. So it would be really, really nice if there were a way to linearize, basically sequentialize our data structure, which is what the virtual machine does. In the virtual machine, all you have is a linear sequence of instructions, and you can jump, of course, between them, but to go from one thing to the next, all you need to do is read the next thing in memory. And then it would be nice if we found a way to access variables without having to do things like compare strings to find out where they are, as well as not having to dynamically allocate memory to get the space to store those variables. And of course, all those problems have already been solved in computing, so we don't have to literally invent them. We can just use solutions that other people have come up with. Don't save. And it turns out that first, to be able to get a nicer memory access pattern, obviously we're just going to use instructions where one comes after the other. And to store variables as well as to get their values, we're going to use a stack. And the way this works is that whenever a function is called, so the stack is one contiguous memory region. And we start at the bottom, and whenever a function is called, it reserves for itself a little bit of memory at the top of the stack, and the amount depends on basically on how many local variables it has, because how many local variables it has and how many temporary values it has to store to do its calculations. And then whenever it calls another function, that function then allocates a little bit of memory on top of that, and so on and so forth. And when a function returns, it basically just removes that piece of memory from the top of the stack, except that no memory actually gets removed or deallocated or anything. The nice thing about the stack is that all you have to do is you need an index into the array that you can increment whenever you allocate a stack frame. A stack frame is the piece of memory that's associated with with one function, and you decrement it whenever the function returns. And so that is why our virtual machine has, I call it value array. Maybe I should call it value stack. But the reason why it's called a value array is because it really is just an array that is kind of used like a stack. And it's used like a stack by virtue of the value stack pointer. And the reason why I'm calling it value stack is because there's actually two stacks. But they go hand in hand. By convention, they go hand in hand. And we'll have to talk about conventions as well. In x86, for example, which is the machine code architecture that we will be compiling to, there is actually only one stack. And that stack is used both for local variables, as well as for, this is another thing that we need, as well as for return addresses. So the thing with calling a function is, when the function is done, you have to know where to proceed with execution, basically where in the code to return to. And in our tree interpreter, what we did was we used the stack of the programming language that we implemented the interpreter in to store that, namely, in our case, C. So recursive function in Simplang would be recursive calls in C. But in our virtual machine, we don't want that. We just want one iterative function that uses some data structure in the virtual machine to represent the recursion. And that's the call stack. So what happens when you call a function is that, first of all, the value stack pointer will be incremented by however much the function needs. And the second thing is that the return address will be put on the call stack. The return address being the index of the instruction that has to be executed after the function returns. Does that make sense so far?
Yeah.
Okay. So then, in addition to that, we have the program counter, which is the index of the instruction that has to be executed next. So now let's look at how this actually works in practice. So one thing that I said is we have to talk about conventions. In particular, the so-called calling convention. The calling convention is a contract between between two functions that call each other, the caller and the callee. And one of the things that they have to agree upon is how the caller passes arguments to the callee. And there can be many such ways. The way in which we do it in this virtual machine, and again, this is influenced by how the virtual machine works, but it's not dictated by how the virtual machine. It could work in a different way. That's just how it's easy to implement and how I've chosen to do it. So what the caller does is it puts the arguments onto the top of the stack in the sequence that the arguments are passed in simplang. So if you have 3 arguments, x, y, and z, then x is passed further down, y is passed on top of that, and z is passed on top of that. And then the value stack pointer is set to the slot that's on top of the last argument. Which means that if your function takes in 3 arguments, then, so these are the 3 arguments, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then the third argument is at index -1 relative to the value stack pointer. And the second argument is at index -2. And the first argument to the function is at index -3 relative to the value stack pointer. So here we see the value stack pointer is at index 3, and the first argument is at 3 minus 3, which is 0. So that is one part of the calling convention. So we're running the program with the arguments 1, 2, 3, 4, 5, 6, and 7, 8, 9. So this is what the value array will look like, where the value stack pointer will point to. And the program counter is 0, because that's where the program starts. Now, our first instruction in our program is an add instruction, and the 0 here is just the index of the instruction. It's just a line number, basically. And the way the add instruction works is that it takes 3 arguments. All of them are relative indexes to the value stack pointer. And what it says is that add the value in the value array at that index, at that relative index, to the value at that index, and put the result at that index. So because our value stack pointer is 3, $0 means 3 plus 0, which is 3. And -3 means 0, and -2 means 1. And so what we're doing is we're taking the value at absolute index 0 and the value at absolute index 1. We're adding them together, and we're putting the result at absolute index 3. And this is another thing that's part of the calling convention, namely that all the space in the value array on top of the arguments belongs to the callee. In other words, the caller must not assume that anything on top of the arguments will have the same value that it had before the function, before it called the callee. And on the other hand, everything that is below the arguments, in this case, of course, there's nothing there yet because this is the first function we're calling, but everything that's below belongs to the caller. So the callee must not modify anything that's below here. And again, that's just a convention. The callee, there could be code in the callee that does that, but it's not supposed to, because that means it doesn't play nice with the caller. And if the caller assumes the callee to play nice, but the callee doesn't, then the program will give you probably the incorrect answer, or it might crash or whatever. Does that make sense so far?
Yeah.
Okay. So here in this in this diagram, I'm already only using the relative index because it turns out that in this virtual machine, only relative indexes are used. So you can't even use an absolute index. So everything is relatively indexed. So actually, our program. What is our program supposed to do? Okay, we don't know yet. We'll see. So the next thing is that we add the third argument to the sum that we have already computed of the first and the second, which is at $0. So we're adding -1, $-1, the third argument, to our previously computed sum of the first and the second, and we're putting it into that same stack slot. And that's allowed. So you can use the same stack slot on the left-hand side as you used on the right-hand side, and that will work as expected. So now we get this. And now let's say we want to add the number 10 to this. There are two steps to this. First of all, we must get the number 10 into one of these slots. And the way you do this is you use the set instruction. So in this case, we're going to use the slot $1, and we're going to set it to 10. So this is what that looks like. And now we can use the add instruction to add the number from before and the number 10, and we're going to put that into slot 0. So there we go. And now what do we do here? And now we multiply the whole thing by 5, I guess. What we're doing is, no, that's not what we're doing. Let's write a function that takes a number and multiplies it. Oh, okay. So we're done with this. We're doing a new. Okay. I'm sorry. We're doing a more complex thing. We're showing how. I wrote this a while ago. I'm sorry. I don't remember everything. We're actually gonna, from this main function, we're gonna call a different function, a function that multiplies, that takes a number and multiplies it by 5. So we're not in this function anymore, right? Forget what's here. Just assume we have one number on the stack. Which is the argument to the function. And because of the calling convention, that number must be at what offset?
So from the example we had so far?
No, if we have a new function.
So -1?
Yeah. So that number must be at -1. And we want to multiply it by 5. So what we need to do is we need to get the number 5 somewhere. We haven't used the slot 0 so far, so we can use that to store the number 5. And then we multiply the 2, and we store the result in 5 in $0. And now we want to return to the caller. And the way we do this is we use the return function, and the return function takes takes a stack slot as an argument, and that is the value that will be returned from the function. So we're returning this product of our first argument and 5 to the caller. And now what we're doing is we're writing a loop that will call this function 4 times on the result we got from instruction 3 above. So the result that we got from instruction 3 above is this. So one thing we can do is we should maybe write a simplang function that does what this program does. So far we have one function that's this function that starts at 12 is let's call it mul5 x equals x times 5. And then we have the main function, which has an x, y, and z, which does something like let sum equals x plus y plus z. And let's say sum equals, well, actually, we're just adding 10, so x plus y plus z plus 10 in. And now we want a loop that calls this 4 times. So what we want is a loop which has a counter and I don't know, p equals sum in. If I is less than 4, then we recur with I plus 1 and mul5 of p. Else we return p. Right? So we're still missing this loop. This is what we're implementing now. So we have the sum, we have our mul5 function, but we don't have the loop yet. So, well, actually, we're counting down here. So maybe I should do it like this. Equals 4, and then if I equals 0. Actually, I can take if I. No. If I, then I recur.
Oh, I guess, yeah. If I and then
I plus minus 1. Okay. So again, where were we? So here's the thing now. My number, the number that I want to use is in stack slot 0. I need another stack slot to store. So this is going to be p, right? Or this is p in the first iteration. But I need another stack slot to store I. So let's say I used $1 for I. Then whenever I call this function, mul5, I need to pass p as the argument. If I call the mul5 function with p in the place where it is right now, then my loop counter would be above that. But I can't have that because, as we said before, when you call a function, whatever is on top of the arguments to the function belongs to the callee. So the mul5 can totally modify, and I should expect that it will modify this number here, or will modify the stack slot. One thing I could do is I could move it up in every single loop iteration, and then move the result back. but I want to be more efficient in the loop, so I'm going to reverse the order. I'm going to move the argument here, and I'm going to use this slot for the loop counter. Does that make sense?
Also, but wait, how do we differentiate them? Because the oh geez, sorry, I have to think about it first. So when we go into the loop, I equals 4 and p equals sum, what if we then call the function multiplied by 5 with the value of I? Because then we would have to reverse it too, right? Do you know what I mean?
Well, we don't. What we want the stack to look like is we want this number somewhere, the value stack pointer 1 above, right? Pointing to 1 above, because that's what the call-it convention says, right? And then we must also not depend on anything that's at the value stack pointer or higher to be the same when the callee returns.
Okay.
So if we called the function and we incremented the value stack pointer just by 1 slot, then it would get this number as its argument. Right? This would be the argument to mul5, which is the correct argument. But the problem is it would destroy this value because that belongs to the callee.
Yeah, yeah.
Does that make sense? No?
Yeah, no, that makes sense. But well, I think, yeah, but you said we can avoid that by just reversing the order. So in the index, relative 0 would be then 10, and in 1 would be 1, 3, 7, 8.
Well, it wouldn't be 10. The 10 is actually just a temporary value from a calculation above.
Well, in that case, then 4.
The 10 we don't need anymore, but we need the number 4.
Yeah.
Right? And we're going to use, so we're going to do away with the 10 by simply overriding it and overriding it with this number. So we're going to move this $1, and then we're going to use this for the loop counter, which is going to be 4 at first.
Okay, and then we increment the stack pointer by 2.
Twice.
No. We do not advance the stack pointer yet. The stack point, we advance the stack pointer when we call the function.
Yeah, but it's going to be advanced twice.
Yes, yes. The stack pointer will then be okay. So let's just look at the code and what the call looks like. So as I said, we're going to move what's in $0. That's our sum. We move that to $1, so it's here now, and we set $0 to I, which is 4, so that's here now, and this is the value stack pointer. Now to call the function, yes, we need to move the value stack pointer up to here, because then this is going to be the first and only argument to the function, and this is going to be off limits to the callee. So mul5 must not modify this; it's not allowed. And at the same time, we are not going to use anything that's above, because anything that's above belongs to mul5. Right?
Right.
Okay. So then, to call the function, what we do is, the first thing we pass in is the index of the instruction where the function begins, and that magically Turns out to be 12, which is exactly where we wrote it. The second argument is by how much the value stack pointer needs to go up, which correctly is 2. And the third argument is the index where the function result should be written to. And that's what the return instruction does. So remember, in the return instruction, we said return, and then it was $0.
Mm-hmm.
The return instruction actually works by looking at the call instruction that called it, and then figuring out where to put the result. That's kind of weird, but it turns out it's very easy to write code for it. So basically, what this function does is it calls mul5, which is at 12, by advancing the stack pointer by 2. And by the way, the stack pointer will also, after the call returns, it will be back where it was. That's another thing that the return instruction does. And we want the result to appear in $1. So basically, after this instruction, $1 will be $1 times 5. We cannot depend on anything above $1 to be at all what it was before. We must assume that it's been clobbered. But anything below should be the same, and the value stack pointer will be at the same place. Make sense?
Yeah. So we also have to make sure that like for instance, if multiply if we have a function multiply with 2 numbers, x and y, and then we pass it. We pass the numbers to it. So in our example with the p and the I, whether we give that function p and I or I and p, well, in which order it is, we have to align the stack to properly. Sorry, I'm having difficulties like just expressing the thought, but just we have to get it in the right order before we can call the function.
Yes. So if mul5 would, for example, also take the argument I first, right?
Yeah.
Then magically, we wouldn't have to change anything in the virtual machine code, because it would be exactly the same code.
Mm-hmm.
Right? Because magically, I comes first, and then there's P.
And so if we did that the other way around,
if we did it the other way around, however, then these two would have to change order.
Yeah.
Not only would these two have to change order, we would also have to change mul5 to use not $-1, but $-2.
Yeah, right.
Because x would be $-2, I would be $-1. Okay?
Mm-hmm.
So this is what we end up with. Well, actually, this is not what we end up with. This is what the stack looks like for the function mul5. Namely, it has its one argument in $-1. This is of no concern to it. And then it does its job. And when it returns, this is what the stack will look like for the main function. The value stack pointer is back where it was. This has not been modified. And here we have the result of the function call. And everything that's above, we can't assume that there's anything of use in there, right? So now we have to decrement the loop counter.
And so where did the 12 come from again?
Oh, the 12 is where our function starts. It's just the line number of the function, basically.
Okay, but then...
and the reason why it's 12 is because the main function actually takes exactly 12 instructions. But of course, you don't know that when you write.
Yes, but
like
here it's...
I magically knew that because I wrote both functions before I wrote the tutorial.
But then the multiply is at 13.
Yeah.
So why wouldn't it be called 13?
Why would what not be called 13?
Call 13. Or well, go back down.
No, 12 is the first line. Is the first instruction of mul5.
Oh, okay, yeah. Okay.
Okay, so we need to decrement the loop counter here. This is what we need to do. So we need to load, or we need to set some stack slot to -1, and we're going to use the stack slot $2. And note that $2 is above this line, or above this line actually. So when we call the function the next time, that $-1 will be overwritten. And so we could have been smarter. So I was kind of smart in one sense, but I was stupid in the other sense. Our compiler will probably not be smart enough to make this optimization, but a smart compiler could have figured out that this value is the same in each loop iteration. So it could have reserved a stack slot before the loop was started and written the -1 in there. And then it wouldn't have to do the set. It could just do the add. Right? But in this case, I just wanted to show what the stupid compiler would do. So a stupid compiler like the one that we're going to write is going to set this value each time. And then it's going to increment or add that to the loop counter, which means it's actually decrementing because it's negative. And then we have an instruction that is jump if 0, which works by giving it a stack slot. And if the value in that stack slot is 0, it jumps to the instruction with the index that's given as its second argument. And that in that case, we're jumping out of the loop. And at the end of the loop, or after the loop, all we're doing is we're returning the value in stack slot 1. Otherwise, we recur.
Good afternoon, everyone.
Oh. Do you hear that?
Welcome to What's New in Swift. I
thought we had another guest. Who wants to tell us about Swift? Yeah. So if we have not jumped, so if I was not 0, then we go back to the beginning of the loop, which is 6, which is the call to mul5. Good so far?
Yeah.
Yeah. And that's basically it. There are a few more instructions in the virtual machine that make it possible to implement all of Simplang. Hello. Oh, I need to save. Namely, we have, so we already talked about the move instruction. We talked about the set instruction. We had add multiply. We also have negate. Now, of course, negate, you could implement negate by using a set to set a slot to -1, and then you could multiply. But I wasn't masochistic enough to do that. We also have not, which also isn't strictly necessary. You can implement not with comparisons and sets. So it's not a minimal instruction set. It has a few things that make life easier for the compiler, but not that many. And in particular, it doesn't have any instructions that there are a few pretty obvious instructions that you could add that would make it a more efficient virtual machine, and we can talk about that later after we finished our compiler. There's control flow, so we talked about jump and jump of 0, and then there's call and return, and then there's two comparison instructions, less than and equals, and maybe the one instruction or the two instructions that are not obvious in their effects are call and return. They are a little bit magical, and that makes it a little bit difficult to implement in the virtual machine, but it makes it very easy for the compiler to generate code. So call does three things. The first of all, we talked about the call stack, which is a stack of instruction addresses that specify where calls were made from. And note that none of these instructions allow you direct access to the call stack. So the call stack is completely hidden behind the call and the return instructions. And this is how it works. When a call is made, the program counter, which is the index of the call instruction that made the call, is pushed onto the call stack. And then this number is added to the value stack pointer, which is, advancing this stack, moving this thing around. And then it jumps to the instruction. And then it jumps to the instruction with that index. And that's all that call does. The main work is with the return instructions, with the return instruction. So here's what the return instruction does. You give the return instruction a stack slot. That's the value that the function returns. First of all, it reads the value that's in that stack slot. Then there's a special case, namely if the call stack is empty, then we've basically, the function that is currently running is the main function. So we end the program and we produce that result, like we print the result. So that's one special case. But in the usual case, if there is a caller, we pop off the index that the call instruction pushed. So now we know which call instruction called us. Now we take a look at that call instruction and we get the number by which we have to decrement the value stack pointer to put it back where it was. right? So now the value stack pointer is where it was before the call was made. So now we look at the number of the destination slot, and that's where the result has to be written to. So that's what we do next. We write the result that we read in the first step, and we write it to that relative stack slot. We have to do that after we've decremented the value stack pointer, right? Does that make sense? Using the new decremented value stack pointer. And then we jump to the instruction after that call instruction. And that's it. So it's not really difficult, it's just a little bit intricate. Does all of that make sense?
So just to clarify in ways we will then implement it.
Yeah.
Are we just going to well, are we just going to like scrap the interpreter and just work from the tree we got from the parser, and then try to?
I wouldn't scrap the interpreter. I would keep the interpreter. Like, don't throw the code away.
No.
In particular, you might want to keep the code just to, first of all, as a reference, and second of all, maybe you wanna benchmark how much faster the machine is compared to your old interpreter. But
sure,
yes,
sure.
we will write the compiler based on the syntax tree that we got from the parser. So we're not going to need, other than for reference and for benchmarking and maybe for looking at it, we're not going to need the old interpreter anymore.
Okay. Yeah.
So the old interpreter will be replaced by the compiler that compiles from the syntax tree to the virtual machine and the virtual machine interpreter. That's the replacement.
Okay.
Do you believe that all of Simplang can be translated to this virtual machine?
Well, I guess it has to, right?
Oh, okay. Maybe I should ask, is it, like, do you have an idea how all of it can be translated? If I gave you a Simplang program,
Yeah.
could you translate it by hand to this virtual machine?
No, might need to give me a few days, but I think I guess it would work.
So we went over implementing loops. We went over implementing function calls. You know how to store variables. You know how to store temporary results. There's not much more than that to it, right?
And arithmetic and everything should. Well, yeah, that's just comparison.
Yeah, there's instructions for all the arithmetic stuff that Simplang does. So
yeah,
that's all there.
Yeah.
Do you feel confident, Pete?
Yeah,
that you could do that?
Just like one thing that there was a point where you said we push the instruction that's like after the, so let's say you make a call.
Yeah.
You push the number of the instruction that comes after your call. But
No.
you said
So
that in the beginning, but it seems.
Oh, okay. Maybe I misspoke. So in most, so on x86, for example, when you make a call, what is pushed onto the stack is the address of the instruction that comes after the call. In our case, we need the call instruction because we're we're taking stuff out of it. So to make things easier, we are pushing the address or the index of the call instruction, not of the instruction that comes after the call instruction. Although, I mean, technically, you could push the instruction after the call instruction and then decrement it here to get the index of the call instruction, right? Mm-hmm. So it's really just an implementation detail, since, as we said, the call stack is not visible at all to the program. It's completely hidden. So actually what goes on in the call stack is completely an implementation detail of the virtual machine.
Mm-hmm.
Mm-hmm. So the assignment for next week is to basically figure out, and it's pretty easy, figure out how to implement the value array and the value stack pointer. And in particular, with respect to the way that the virtual machine instruction interoperates with the array and the value stack pointer. Meaning that it uses relative addressing, right? We always give relative offsets. It increments and it decrements the value stack pointer. And just implement that. And then, write a few tests, which in this case, I can't write tests for you because it's an implementation thing. Like we don't have a way yet. Before you've implemented any instructions, I can't write a test case for you because it's your code and your internal interface. But just make sure that the basics work.
Okay.
Sounds good?
Yeah.
All right. Cool. Talk to you soon then.
All right. Bye.
Bye.